Okay. Hello everyone, my name is Abdulaziz Ria here, and today I'll be presenting our work, Aero, Augmented Replay for Robust World Models. At high level, Aero is a continual reinforcement learning method that keeps or helps an agent to learn a sequence of tasks without forgetting the earlier ones. And it does this while using only modest fixed amount of memory. So over the next few minutes, I would explain the problem we are tackling, the neuroscience idea that inspired our solution, and how the method works and what we found in our experiments. Reinforcement learning works very well in single fixed environment, where one task is learned and nothing changes. But in many real settings, the agent faces sequence of changing tasks without clear boundaries or tasks labels, and must keep adapting over time. The key challenge is balancing three goals: retaining old skills, which means stability, learning a new task, which means plasticity, and transferring knowledge between tasks. These goals conflict. The main failure mode is catastrophic forgetting, where learning new tasks causes old ones to be overwritten. The core problem is simple. Intelligent agents should learn a new task without forgetting old ones. Humans do this naturally, but neural networks often don't. They overwrite the old knowledge when they learn new tasks, a problem known as catastrophic forgetting. In continual learning or continual reinforcement learning, the agent faces a sequence of changing tasks without being told when tasks switch. It must keep learning while remembering everything it has seen so far. So why continual learning is so difficult? It comes down to fundamental trade-off. A good continual learner needs three things at once. The first one is stability, meaning retain performance on past tasks. It must retain good performance on the task already learned. The second one, plasticity, which means it must still be able to learn a new task efficiently. And the third one, transfer, which also means it should reuse what it already knows to learn a new task faster and even improve on old ones. The problem is these goals pull against each other. If you make the network very stable so it never forgets, it also becomes rigid and can't learn anything new. If you make it very plastic, it learns fast, but it also forgets fast. This tension is known as the stability plasticity dilemma. And reinforcement learning makes this even harder than the supervised case. In supervised learning, you can often just reshuffle the replay a fixed data set to smooth out the non-stationary, but in reinforcement learning, you usually can't. The data is streamed as the agent acts. As the agent acts, task may never repeat, and the environment itself is non-stationary. So how have people tried to solve this? There are three main approaches. The first one is parameter regularization, like elastic weight consolidation, which protects the most important weights from changing. The second one is modular architecture, like pathnet or progress and compress, which allocate different parts of the network to different tasks. The third one, and the most relevant one here, is the replay, where the past experiences are stored and reused during the training to prevent forgetting. Replay is very effective, and selective replay can reduce forgetting without storing everything. However, naive replay does not scale well. Storing full histories become invisible, especially with high-dimensional data like images. And large-scale reinforcement learning systems make this memory cost clear. More recent work extends replay to model-based agents, including continual world models. But memory-efficient replay in this setting is still underexplored. So the key question is, can we get the benefits of replay without the large memory cost? and without requiring task labels. So our solution is inspired by neuroscience, specifically the complementary learning system theory. The brain uses two systems, a fast one, the hippocampus, that quickly stores recent experiences, and a slow one, the neocortex, that gradually integrates them into long-term knowledge. The key idea is that the hippocampus replays experiences to the neocortex, preventing forgetting. The neocortex can be seen as the slow predictive system, effectively a word model. This motivates Aero. Instead of using replay to train the policy, we use it to train the word model. This is more biologically aligned and, as we show, effective. So let me briefly explain the backbone. A word model learns to simulate the environment by predicting the future observation and rewards from the agent's action. A dreamer uses the recurrent state space model, or as you may know it, RSSM, with deterministic and stochastic latent states to encode observation and reconstruct both images and rewards. With a trained word model, the agent can learn entirely in imagination by generating rollouts, making the training highly sample efficient and naturally off policy. This word model and actor critic setup is directly inherited from Dreamer version 3. It is the foundation of our replay method builds on. Our contribution is Aero, which extends the Dreamer version 3 with Dawa buffer replay mechanism inspired the brain's fast slow memory system. Instead of single replay buffer, Aero uses two. The first one is the short-term first in, first out buffer that stores recent experiences, just like hippocampus, and a long-term buffer that maintains a diverse, representative set of all past experiences, just like the new cortex. Importantly, it requires no task identifiers. The key point is that we do not introduce a new sampling method. We just show that this simple fast slow memory split inside the word model is enough to turn the recency biased agent into an effective continual learning under a fixed memory budget. The core of Aero is a dual replay buffer with a fixed memory budget, about 524,000 observations, which is half of what Dreamer version 3 uses. All methods that also include Dreamer version 3 and TES SAC gets the same budgets. So performance differences comes from memory usage, not the size. The buffer has two parts. The first one, as we mentioned it before, the short-term first in, first out buffer that stores the recent experience and helps the fast adoption. The second one is the long-term buffer that keeps diverse representative sample of all past experiences using the reservoir sampling, which helps preserve the old knowledge and reduce forgetting. We sample from both buffers during the training. In practice, we store experiences in fixed chunks with the 512 steps instead of full episodes, which improves diversity and makes the long-term buffer more representative. So now the experiments. We evaluate Aero in two settings. The first one is task without shared structure. We used 6 Atari games with very different dynamics and no overlap. The second one is tasks with shared structure, and here we use 6 Procgen CoinRun variants where visual and behavioral changes allow transfer. In each settings, we test 3 training setups. The first one is a fixed task order, and the second one is reversed order for robustness, and the third one is the 2 cycle settings, where the agent revisits all tasks twice under the same budget. We compare against 2 baselines. all using the same replay memory size, Dreamer version 3 with a single buffer, and a strong model-free baseline, which is the SAC or the specific variant TAS SAC. We ran all experiments over 5 seeds and reported the median performance with interquartile ranges. So how we measure success? Performance in continual reinforcement learning is multidimensional, so we report several metrics instead of one number. We measure forgetting and forward transfer. Forgetting measures how much performance drops on all tasks, while forward transfer measures whether the earlier task helped learning new ones. We also use stability plasticity metrics like the average accuracy, the minimum accuracy, and the worst case accuracy, which captures both current performance and the worst degradation across past tasks. However, in the 2-cycle settings, we all report the maximum forgetting and recovery, in addition to what mentioned before. To measure how much performance drops and how much is regained when tasks are revisited again. Now the results, starting with Atari, which is the hardest settings with no shared structure. If you take a look at the figure on the left, we have the normalized performance, and we have the 3 rows, A, B, C. The first row, which is A, this is for the default order of tasks. The second one is for the reversed order of tasks. The third one, which is C, is for the 2-cycle training setting. So we can see here our arrow almost eliminates the catastrophic forgetting, regardless of task order. Unlike Dreamer, which learns a task and then quickly forgets it when switching to a different task or the next task, Arrow maintains performance across tasks. The clearest result is the worst accuracy, or the worst case accuracy, WCACC. Arrow is the only method with the positive WCACC. While Dreamer and SAC are negative, showing the best balance between learning and retention. There is a trade-off. Dreamer version 3 sometimes reaches a higher peaks and transfer slightly better because it fully specializes on each task. Arrow trades a bit of peak performance for much better retention. For the SAC or the TAS SAC, low forgetting is misleading. It simply doesn't learn Atari well at this budget, so there is a little to forget at this point. That's why the WC or the worst case accuracy is more informative than forgetting alone. Now the easier setting, CoinRun, where tasks share strong visual and structural similarities. As expected, all methods forget less than in Atari. So the key question is stability, plasticity, balance. Arrow achieves the highest worst case accuracy in all configurations. Forgetting is almost zero, and in the reversed order it even becomes slightly negative, which means a backward transfer. Arrow learns a bit more slowly on each task, which is the trade-off for better retention. Another benefit is stability. A Dreamer shows a high variance and sometimes low minimum performance, while Arrow's replay buffer stabilizes training and keeps performance always high. If I had to highlight one result, it is the 2-cycle setting, which is the most realistic since real systems revisit the same task over time. In this settings, Arrow's maximum forgetting is much lower than Dreamer. Almost zero in CoinRun and about an order of magnitude smaller on Atari. Arrow is also the only method with the positive worst case accuracy in Atari. Another key result is recovery. When tasks return, Arrow quickly regains performance and often surpasses its previous best. Overall, Arrow shows its biggest advantage in this realistic, repeated task setting. So, does the FIFO LTDM ratio matter? We tested whether the 50-50 split between the two buffers is important or not. We vary the ratio from mostly FIFO, which is the AR25, to balanced AR50 to mostly long-term AR75, while keeping the total memory fixed. The results show a clear trade-off. More long-term memory reduces forgetting, but slightly hurts the plasticity, while more FIFO improves learning speed, but increases forgetting. The balanced split sits in the between. Importantly, no single ratio consistently wins. The main takeaway is that the dual buffer design matters more than the exact split, and 50-50 is just solid default, not a tuned choice. Stepping back, our results show that the augmented replay toward model is a strong approach for continual reinforcement learning. It is more stable than baseline and achieves better balance between learning new tasks and retaining old ones, even without task identifiers. It is also complementary to existing methods. Instead of changing the model parameters or policies, we focus on what experience is stored, so it can be combined with other approaches. There are still limitations, of course. The buffer split is a fixed. Reward scaling requires collaboration, and any finite memory will eventually forget if tasks are never revisited. We also only tested a limited number of tasks ordered due to compute constraint. To conclude, we introduced Arrow, which extends a word model with a dual buffer replay system, a short-term buffer for recent experiences, and a long-term buffer that preserves diverse past experiences, inspired by the fast and slow memory in the brain. With a fixed memory budget and no task identifiers, Arrow significantly reduces forgetting while maintaining strong forward transfer. In the two-cycle setting, it achieves almost zero maximum forgetting, unlike the baseline. Overall, the key message is that combining model-based reinforcement learning with efficient brain-inspired replay is a strong approach for continual learning. That brings me to the end. Thank you very much for your attention. If you'd like to read more about the paper, it is available on Open Review. You can just scan the QR code on the right. And if you want to reproduce our results or build on the method, the full implementation is publicly available. You can just scan the QR code in the bottom, and it will take you to our GitHub repository.